We know of 118 elements on the periodic table. Yet, if you look at the natural world, you will rarely find an isolated atom existing entirely on its own. A solitary atom is naturally volatile. The laws of physics drive matter towards its lowest possible energy state, a state of total stability. Because these high-energy atoms are unstable, they are forced to interact. The complex world around us exists because atoms are constantly seeking the balance that only comes from combining. There are a few rare exceptions to this instability. Elements like neon and argon, the noble gases, are inert and perfectly stable existing alone. Their stability is a result of their electronic configuration. These atoms possess exactly 8 electrons in their outermost valence shell, which creates a complete low-energy structure. In 1916, scientists G.N. Lewis and W. Kossel observed this lack of chemical activity in noble gases and deduced the underlying rule governing how all atoms behave. They developed a shorthand called Lewis dot structures to track atomic behavior. By stripping away the inner layers, we can focus entirely on those critical outer electrons. Since most elements lack this 8-electron configuration, they remain in a state of high-energy tension until they bond with other atoms to fill their valence shells. The first strategy is electron transfer. This is driven by electronegativity, a measure of how strongly an atom pulls outer electrons toward its own nucleus. Take sodium and chlorine. They represent an extreme inequality in pulling power. Sodium has 1 extravalent electron it can easily lose, while chlorine is exactly 1 electron short of a full octet. The transaction is total. Sodium donates its extra electron to chlorine, allowing both atoms to reach their most stable configuration at the same time. This transfer changes their physical state. The atoms become oppositely charged ions, which attract each other with immense electrostatic force. Ionic bonds achieve stability through this surrender and capture. It results in the rigid, crystalline structures we recognize as common salt. But what happens when nonmetals with similar electronegativities meet? In this case, neither atom has a strong enough pull to steal an electron from the other. The solution is mutual sharing, creating a covalent bond. Look at carbon and hydrogen. Carbon needs 4 electrons to complete its octet, while hydrogen needs just 1 to fill its much smaller single shell. A single carbon atom shares pairs of electrons with 4 separate hydrogen atoms. This allows their electron clouds to overlap, satisfying the requirements of every atom involved. Covalent bonding reaches stability through cooperation. These shared connections form the foundations of all complex organic matter. Lewis structures are useful blueprints, but they are only 2-dimensional. In reality, these bonds occupy physical space. This is explained by VSEPR theory. Because electrons all carry a negative charge, the shared pairs in a covalent bond strongly repel one another. This repulsion forces the bonds in a molecule like methane to push apart as far as geometrically possible, bending the molecule into a 3-dimensional shape. This physical repulsion dictates the geometry of our world. It determines the 3D structure of everything from the way water flows to the twisting helix of our DNA. There is a massive payoff to this interaction. When bonds form and atoms finally reach their octet, they release energy into the universe. This release is the physical sign of a transition, moving from a state of volatile potential to one of anchored stability. Every solid object we touch and the very air we breathe is the result of these invisible particles successfully reaching their lowest energy state.